to talk about Bayes' theorem, I'm going to talk about my favorite kind of example, which unfortunately is a morbid example of diseases. Okay, it's not death this time, it's diseases. And because of lack of creativity and also for convenience, the disease we're going to focus on is going to be called disease A. Disease testing for disease A. Yes, during COVID, we couldn't seem to help talking about it in terms of COVID, but I don't want to talk about COVID anymore. So it's back to disease A. What is disease A? I'm not saying. Maybe it's deadly, maybe it's not. Okay, it's nicer to pretend it's not. But what I will say is it's rare. It's a rare disease. How rare is rare? Well, it could be 1% of the population has disease A. Maybe 1/10 of 1%, maybe even 1/100th of 1%. Yeah, let's go extreme here. 1/100th of 1% of the population, meaning say the US population or the world population, has disease A. It's a rare disease. Oh, I should capitalize disease. Disease A. That's its name, disease A. Okay. So it should be capitalized. And somehow this is known, but scientists are trying to develop a new test to detect if somebody's got disease A that they hope will be better than the old test. There's a test, a new test for disease A. This new test correctly says, hey, you have disease A, when you really do have disease A 99% of the time. The probability that the test comes back positive, I'll write that as lowercase POS. I could put a plus sign for positive. Given that you have disease A, if it's known you have disease A, positive means you have it. So that's actually a bad thing. Don't be thrown off by the word positive. Is 0.99. Sounds pretty good, right? That's called a true positive. It would also imply that the false positive rate when you do not have disease A is 1 minus 0.99, 1%. And it also correctly comes back negative, complement of positive, when you do not have disease A, say 98% of the time. Pos prime is the complement of positive. You could call it neg for negative if you wanted to. Negative is a good thing. It means you don't have disease A, according to this test. That's equivalent to saying it's going to come back positive, or excuse me, negative when you do have disease A 2% of the time. Here's the question. You go get the test. You don't know if you have disease A or not. It comes back positive. What's the conditional probability that you have it? I hope you would not say 0.99. Because, right, I emphasized earlier today that if you switch these things around, you're probably going to get something different. So is it 0.98, 0.97, 0.96, maybe 0.999? Before we try to answer this, let's try to get a little intuition. Intuition with a Venn diagram, where, roughly speaking, I try to make events have a size matching their probability, including this very low probability here of 0.0001, one out of, what's that, 1/10,000th? One out of every 10,000 people has disease A. Oh, in a country of 300 million people, how many people would have it? 1 out of every 10,000 would be 100 for every million, 1,000 for every 10 million, 10,000 for every 100 million. Say 30,000 people in the country have it out of 300 million. We have more than 300 million in the country, but most people don't have it. Okay, pretend this box is everybody in the country. Let me make a box for disease A that is supposed to represent 0.01% of the area. Now, okay, if I was going to draw that literally, I'd have to draw a really tiny box. Barely be able to see it. Okay, I'll make it bigger than that. I'll still make it small, but I'll make it bigger than that. So this box represents those people who definitely have disease A in the whole country. This conditional probability here, the probability of coming out positive if it's known you have disease A, effectively means, if you think in terms of area, that of this small box, most of it is taken up by people who will test positive. 99% of that box. This one, the 1%, means that the positive blob is going to make up 1% of the area of everything outside of A. Okay, so I'm not going to make it very big. I'll just say it like that. So it's making up most of the area in A itself, but a small part of the area in A prime. Everything out here is A prime. Complement of A. Now, I want to answer this probability question, where it's known a person comes back positive. It's known that they are in the red blob somewhere. What are the chances that they're in the small box? Again, I haven't drawn things accurately, but I hope it's reasonable to see it may not be a big number. The area in the blue bounded box here, as a proportion of the red area, could be moderate in size or even small. I didn't try to draw it super accurate, but it's conceivable it could be a small answer. All right, how do we find it? What is Bayes' theorem? Here's what we want to find. Go back to the definition of conditional probability, which reminds me, I forgot to mention something. Based on this definition of conditional probability, we can also write down a general multiplication rule, not just a multiplication rule for independent events. Assuming P of B is non-zero, this makes sense. And you could multiply both sides by P of B and say the probability of A intersect B is the conditional probability of A given B times the probability of B. That's called the general multiplication rule, and it works even when the events are not independent. Got to mention it. You should know this, should be able to use it. And by the way, the roles of A and B are symmetric. This also equals the conditional probability of B given A times the ordinary probability of A. You know, they're just arbitrary symbols anyway, so it shouldn't matter. If A and B are specific events, the individual numbers that are getting multiplied will be different, but the product will be the same. Anyway, coming back to Bayes' rule here in the context of this problem, I need the formula for conditional probability. In this context, it's going to look like this. But how do I use it? Do I have these probabilities anywhere? I got these four, and I also have this one, which is really the ordinary probability of A. I don't seem to have numbers there that I need. So what do? That's why I needed this. Why I needed this general multiplication rule. For the top, I use the general multiplication rule. Now I could use it using that quantity right there. In fact, I could write the top as the product of these two things. But that would be counterproductive because I don't know that. That's what I'm trying to find. So instead, use this formula where you switch the roles of A and pos around. Use this one. And I do know that, and I do know that. Those are both on the previous page. These two numbers. I'm using the general multiplication rule here. What about the bottom, though? This is the hardest part of Bayes' theorem right here. What I want to do is I want to break up the positive region here, what's shaded red, into the union of two mutually exclusive events. Pos intersect A and pos intersect A prime. And then use axiom 3 to write this as a sum. But how do I find those? I use this multiplication rule again. In fact, this one right there is the same as that one right there. Those two things I'm pointing at are the exact same probability. So what goes here is the exact same thing you see there. And what goes here is something similar, except replace A with A prime, the complement of A. And that, in essence, the equality of this with this is Bayes' theorem in this example. It can be generalized. In fact, it can be generalized to situations where you got a bunch of events that the thing in the bottom could be thought of as a union of a bunch of mutually exclusive events, and you could have more than two terms in your sum in the bottom. There's one example in the book like that. I think it relates to blood type. You should make sure you study that one. As far as us finishing the problem, we do all know all these numbers. Before I plug the numbers in, I'm going to also show you that you could help avoid mistakes by drawing a tree diagram here before I plug the numbers in. You can organize your work for this kind of problem, and I'd recommend it, in fact, with another tree diagram. Label the branches with probabilities. And here's what they are. Multiply the numbers along the branches to get the, well, essentially the products that you see here. By the way, notice I never said anything about independence. When we made tree diagrams before, including 20 minutes ago, we assume independence. I'm not assuming independence here. I'm using this general multiplication rule that applies even when your events are not independent, as they're not. A and pos are not independent events here. I'm using the general multiplication rule. I'm going to multiply along these branches. 0.0001 times 0.99 is well, in scientific notation, it's that. And without scientific notation, it would be 0.000099. Product of these two. I actually don't need to compute, but I'm going to do it anyway, is even smaller, 0.000001. Product along those two, 0.9999 times 0.02 is 0.019998. And 0.9999 times 0.98 is 0.979902. If I didn't make a mistake, these should all add to 1. As far as what we need for the formula up here, it's the ones that involve pos, not pos prime. Those two. This becomes 0.000099 divided by 0.000099 plus 0.019998. That's 0.000099 divided by something that's still small, but on a relative scale, it's significantly bigger, 0.020097. Both of those are small numbers, but the one on the bottom is many times bigger than the one on the top. And therefore, this is going to be a small probability. About 0.005. In other words, about 0.5%. Less than 1% chance of having disease A, even though the test came back positive. Wow. If I've not made a mistake. This will definitely happen in situations where the disease is rare. Even when the test, according to these numbers, seems good. The false positive rate is 1%. The false negative rate is 2%. Seems good. But because it's so rare, even if the test comes back positive, you have a very small chance of having it. Now, 0.1/2 of 1% is much bigger than 1/100th of 1%. In fact, it's 50 times bigger. Your chance did go up by 50 times than if you didn't get the test before, from 0.01% to 0.5%, but it's still small.